So a lot of times in physics, we're asked to look at graphs and figure out what is the equation that, or the general equation that governs that graph. So this little exercise just has us graphing, just sketching really, what is the shape of these graphs. So just going through these. Equation 1 says it's y is equal to ax minus c. Well, if I look at a graph of x versus y, if a, b, c, any of these values other than x and y are constant positive values, that means this is a line, a straight line in fact, where we get y is equal to mx plus b, our general form of our line. We see x is to the first power. There's no exponent, so it's to the first power. A is a positive value, so that means it's a line with an upward slope, a positive slope, and a negative y intercept. So I am going to look at this graph. This value right here is minus c, and the slope of this is going to be a. So this is what my first graph looks like. My second graph, y is equal to ax squared plus bx minus c. It's a little bit of a harder one to do. But I know that this graph has, when x is 0, my positive x, my positive y, when my positive x, or when x is 0, I'm at a value of minus c. So I know that I'm at a minus c value down there. And I know that this is a parabola that goes in the upward direction. As I get any value of x, these values are going to get larger. If I go negative, yeah, I get a little bit of a negative b. But I know this is going to curve upward. So the graph of this one is going to look something like this. It's going to be offset just a little bit in the negative direction where its center point is. But it's going to go through the point negative c, and it's going to have an upward curve to it. Third equation, let's do the third equation in green, is actually a simpler one. Probably should have done that one first. X and y is my graph. I have y is equal to bx squared. If x is 0, y is 0, so I'm at the origin. Positive value, this is an upward parabola that goes in that direction. Fourth graph looks similar to the third graph when you first look at it, but you actually have to be careful. The fourth graph on this one, y is equal to b2 times x to the minus 2. So x and y. This equation can be written as b over x squared. So it's not a parabola. It's a 1 over x squared function. Well, if b is a positive number, x squared is always a positive number. This thing is always going to be a positive value. And if x is really large, b divided by a very large number is essentially 0. So as it approaches infinity, it's going to be 0. As it approaches negative infinity, it's going to be 0. So I know I'm going to have asymptotic behavior at infinity on both ends. As x gets smaller, the fraction b over x squared gets larger. So this value gets larger, larger, larger. Same thing in this direction. We get asymptotic behavior along the y-axis and on the x-axis. So this thing will never hit 0. At 0, 1 over 0 is undefined. So this is where we get this asymptotic behavior with y equals 0, or x equals 0. This is what the graph looks like. And the last two, sign of those, I'm going to grab another piece of paper and work these out. So let's do these in blue. 5. Five is x and y. 5 says we have a sine of x plus c. Well, this plus c part right here, I know I have some sine function that varies up and down. It's multiplied by some value a. So sine is going to go between the numbers of 1 and -1. So this value right here is going to go between positive a and negative a. It's going to vary up and down. But we're always going to add in some value. So value of c is going to be up here. It's a sine function, so it's going to start at what we would originally call our 0, but we're shifted up by some offset, and it's going to go up some value over and over. Where c is its original starting position, and a is how far from that center C position is. So this is the case if C is greater than A. This thing could stretch up further up and down depending on if A or which one's larger, A or C. But what happens is this thing will vary sinusoidally. It looks like a sine function. It varies between the points A and negative A, but it's offset by a value of C. And last but not least, x and y, a sine of x plus c. This one, the c value is no longer a y-intercept. It doesn't tell us when x is 0 what happens. This actually is what we call a phase shift. So if we remember this value is still going to vary between negative a and a. The sine function will vary between -1 and 1. So this whole function here will vary between a and negative a. But instead of starting at 0, we're going to be shifted by some value. So I'll have a sine function that varies, that is shifted by some value related to c. So it's going to be shifted over by some phase shift. And how much it's shifted over is based off of how large c is. And when you actually get to this part in physics, this is actually one of the harder parts, but it shouldn't be too bad to go through. You just have to remember that the sine function varies every 2 pi radians. So how much the shift is, it's related to c, but it's not actually equal to c. But again, goes between a and negative a, and works out pretty well. And one thing I'll say right here is I wasn't very careful. How fast these things wiggle up and down should actually be the same for both of these graphs. They both have the same frequency of oscillation, or they wiggle in the same rate. So after 2 pi, from here, up, down, up, this value right there is 2 pi radians. This value to here is 2 pi radians. So they should be the same looking graph, just shifted a little bit in both cases.